Okay, so we are speaking about the Yassine, Clementi, Gottardi model of incomplete markets and firms' corporate structure, financing, financial structure. And we had ended with our restrictions on the pricing functions that related to big C's. These are equilibrium objects. We don't know what they are yet. We're going to have to figure out how to compute them. But the individual firms, in effect, know what they are because they know what these pricing functions are. And these pricing functions look like this. So the market confronts the firm somehow knows that it faces this pair of functions. And they're all about, for us, describing some things of consequences of a firm that if it actually deviates from its equilibrium choices, what's going to happen. And then we have a special quantitative example class of examples that we're going to take following Yassine and co-authors, where both types of firms hold equities, both types of consumers hold equities, but only consumers of type 2 hold debt. And the consequence of that is it's going to lead to these restrictions on the pricing functions. It's the type 2 consumers who are effectively, quote unquote, pricing the debt. And it's both the types 1 and 2 consumers are pricing the equity. So their stochastic discount factors are somehow agreeing over subsets of the epsilon space. Okay, so we can rewrite those pricing functions. We can rewrite this as follows. Price of equity is going to just be equal to, equity only pays off if epsilon comes in high enough to render the quote unquote representative firm non-bankrupt. I'm sorry. So an individual firm non-bankrupt, it's going to only pay off, and so we just integrate over this, and this is true. This is going to be true. This is actually identifying the subsets, the subspace of the epsilon over which the two stochastic discount factors agree. They don't agree globally on epsilon, but they agree over this small part. So that's the price of equity. And here's the price of bonds. Only the type 2 people hold bonds, and we just integrate over the two parts. If what bonds pay off is this, if the firm's bankrupt, and they pay off this if the firm is not bankrupt. So that's what these equations say. Okay, so now we turn to the firm's optimization problem. Okay, and let's start staring at it and looking at it. The firm's optimization problem wants to, as we said, it faces the equity pricing function, and it faces the bond pricing function. It wants to choose how much to invest and how much how many bonds to issue. And now its investment decision is going to interact with its financing decision in a way that we saw it did not do in the complete market setup. The firm actually didn't care whether it issued, it had big indeterminacy whether it issued bonds or equities. Here, and it could decide its capital before it decided the mixture of bonds and equities. Here's not true. So if we take first order conditions with respect to K and B, we get these conditions, and now you'll see the firm is differentiating these valuation and pricing functions in order to determine. So those derivatives end up here. So we check to see that I did these derivatives right. Okay. So now we have to do some work. We're going to use, we want to evaluate these derivatives. And our secret weapon there is going to be the Leibniz integral rule, which it's beautiful. It involves, reason we need Leibniz rule is if we look here, epsilon star, epsilon star appears in that integral, but epsilon star depends on K and B. So when we differentiate Q, with respect to K and B, it's not just here, it appears in the limit. And that's what Leibniz rule tells us how to do properly. So I'll let you check that out and get comfortable with Leibniz rule. Okay, so as I said, we're combining ourselves. What we do is we confine ourselves to a special case in which both types of consumers hold positive equities, so that these things are related to rates of intertemporal substitution for both agents. And then once we do that and recognize that, we end up getting these two equations. We get two equations in. So what we've done here is we've rolled up our sleeves and we've used these integrals, these Leibniz rules, and we've gotten the pricing functions out directly in favor of the things that determine the pricing functions, the big C's. So when we do that, we get first order condition for K and a first order condition for B. And there they are. So if we knew the C's, the big C's, if we knew these two big C's, that's which we don't yet, but if we knew them, those are two equations that determine K and B that we want to solve for the firm's optimum problem, for the firm's optimum decision. Okay. Okay. So here's where I'm going to actually refer you to. Actually, I refer you to this quantecon lecture that I'm taking this from, because now we want to worry about computing an equilibrium, and now we can't use, in a simple way at least, the trick of that we used in chapter 9 of RMT, or that's used in the Cass-Koopmans model, or it's used widely. It's used in the real business cycle model, where we can compute a competitive equilibrium by first solving a planning problem. Not here. And the incomplete markets kill that. If there's a planning problem, it's a much more complicated one, and I don't know what it is yet for this model. Um, that's kind of a frontier area of research that a small number of people work on, trying to find planning problems that'll solve that for whose allocations will be allocations for an incomplete market competitive equilibrium. Just a couple papers on that, but that's not what we're going to do. We're going to have to do is write down a system of nonlinear equations that characterize the equilibrium conditions and solve them. So BCG give us some hints. They say if the price checkers corresponding to the plan chosen by firms in equilibrium are correct, that is equal to the market prices, those things, it is immediate to verify the rationality of the conjecture coincides with the agent's Euler equations. Okay. That's a very concise sentence. So here BCG are describing how they go about verifying that when they set little k equal to big K from the firm's first order conditions equal to the big K, big B, big C that appear in the pricing functions, then the household Euler equations are satisfied if little c's are equated to big C's. And the firm's first order conditions are satisfied for KB. And finally, check is equal to this, and check is equal to that. That's how they go. So I'm going to skip over the next part of this. So we do some pseudocode that we've taken guidance from BCG's paper, but we probably deviated at some points. So pseudocode is just something you'd give to a programmer. So what's going to be in the rest of this presentation is I'm going to flash by the pseudocode. You could read this if you're interested in computations. So what you'll notice is it's lots of steps, and it's iterative and involves nested loops. And we've created a Python class that will actually do this. And this tells you the methods that are available in the class. So you could figure out, you could play with this if you want at your leisure. It's available at quantecon. So here's the code. I'm going to flash by it. And now this actually shows you something we did. So we set up an example. I'm just going to flash by here, and here's what I'm going to show you. So this is kind of a key graph. So in the Python code, if you note it, you could actually turn this graph around. So what's here on the X, Y, and Z plane is the firm's choice of this is designed to show at the equilibrium pricing functions that we've computed. At the equilibrium pricing functions we've computed. We're going to graph on the floor of this the capital little k, the little b choice of the firm. Okay, and what's on the y, and then what's on the y-axis is the value of the firm. That's what the firm wants to maximize. So the firm wants to pick a capital and a bond, a debt level that's going to maximize the value of the firm. And something striking happens here. What does that red dot mean? Let's see what it says. The red dot in the above graph is both the equilibrium BK chosen by a representative firm, okay, in a rational conjecture, rational expectation, and the equilibrium big K chosen, big B, big K chosen by the aggregate of all firms. Okay. So it's both. So that red dot that's the equilibrium big K, big B. But what you'll notice about it, there's something striking, and it relates to Modigliani-Miller. And here, at some point, I'm going to have to get some lessons from Basine, Clementi, and Gottardi, because what you'll notice here is if we turn this around, and you can, this maximum in this direction, that's unique. What the firm wants to do, what the individual firm wants to do is unique. So there's a unique optimizer with K, but in this rational conjectures equilibrium, it's true the firm is perfectly happy to set little b equal to big B, but turns out there's a ridge. It's kind of indifferent moving along here. And if it's the only firm that does it and it's a measure zero, that's fine. So in equilibrium, this is true. So there's this ridge. So we might read this. It's sets a positive measure of firms. They're not deviating. That's just a set of measure zero of firms can deviate along this ridge and not affect things, as long as the average is there. So there's something subtle going on. So it looks to me like within this equilibrium, there's a qualified Modigliani-Miller theorem that says the particular firm's individual firm's value is independent of how it mixes its financing between equity and bonds, so long it is not what other firms do on average. So the market's financial structure is determinate and sits at the red graph. So there's a subtle difference in, there's not a classic Modigliani-Miller theorem here, but maybe there's a model, a modified one. So we do more things in this lecture, which you could go and read. You could read something here where we have a strategy for checking the stability of an equilibrium. But the stability of an equilibrium is a topic that people like Arrow and Hurwitz and Samuelson were really interested in a long time ago. Not that long ago, but I'm not going to take it up here. You can read it in the rest of this lecture if you want. So I guess the concluding thing I want to say is this model is a laboratory for doing lots of things about corporate finance. And the paper by Basine, Clementi, and Gottardi has a number of really insightful things to teach us. It's a model which generates in equilibrium disparate stochastic discount factors, and in a determinate way, and that's a frontier issue in modern macroeconomics, because in incomplete markets models, there are the telltale sign is that there's multiple stochastic discount factors, and then the question is lots of times is well, which ones do you use to evaluate certain kinds of prospects and assets, and that's an issue that you're going to see, and there's plenty of papers, including ones I've written or been co-author on, in which we just say we're going to make an arbitrary decision. We're going to make something up, and one message of the Basine, Clementi, Cottardi paper is that, well, they have a structure where you don't have to do that, and it matters. Their later part of their paper also shows that firms kind of, when they design their financial structure, they're actually, it's as if they're within this rational expectations equilibrium. It's as if they're catering to certain types of consumers. So different firms may choose to pitch their liabilities to segments of the market that want to hedge because of the correlation of their own non-financial income with the financial with the financial returns of the firm. So so later at some point, if you read the Basine Clementi Cottardi paper, especially the later parts of it, you'll find many rich potential applications.